the National Cheng University, Taiwan, and he would be talking about the temporal quantum steering and its applications. And you will be 50 minutes for the talk and 10 minutes for discussion. So first, Cheng.
So thank you for the introduction. So first of all, I would like to thank the organizers for giving me this opportunity to have a talk here. Then the talk today is temporal quantum steering and the application. I'm from Taiwan and National Cheng University, and the center, we have a new center we call the QFort. So in the beginning, let me use a little bit of time to show you where I am. So this is Taiwan, next to China, and if you enlarge this, so Taipei you may know, and I'm in the Tainan, the southern part of Taiwan. And actually, Tainan is the first city of Taiwan. Around 400 years ago, the Dutch people came and they left a fort. We now call it Amping Fort. So before starting, I would like to thank to my collaborators and Dr. Neil Lambert, Frank Nori at Riken, and Adam at Poland, also my colleagues in Taiwan, so Professor Yueh-Nan Chen, my postdoctor, Dr. Huang Yuku, also my two students, Lin Zhendong and Huang Yide. And in this talk, I will not only show you the theory about the temporal steering. In the second part of the talk, I will show you we also run some experimental result on this IBM Q and Iron Q, these quantum computers in the cloud. So as we all know that this Google 2019, they have demonstrated quantum supremacy using a programmable superconducting processor. And also later last year in China, Professor Jian Weipan and his group, they have also demonstrated this strong quantum computational advantage using this superconducting quantum processor. Okay. Then this powerful quantum computing ability comes from, actually the essential part is the quantum correlation. So speaking of this quantum correlation, so we can start from this Bell's inequality. You know, when we learn quantum mechanics, you see we have the Bell's inequalities under two assumptions, locality and realism, right? So imagine in the central source, and you create two particles, and one particle sent to the left-hand side, then the other particle sent to the right-hand side. Okay, so on the left-hand side, you can do some kind of measurement, say capital A or small a measurement on the particle. So on the right-hand side, you can also perform a different measurement, say capital B and small b measurement, right? So this measurement, for example, could be, you know, you measure the direction of the spin, right? Could it be X, Y, Z direction? So under these two assumptions, locality and realism, okay? So if I say the measurement outcome is, if I measure spin up, then I assign a value +1. So if the measurement outcome is a spin down, then I assign it a value -1. So this for measurement outcome could be, you know, 1 or -1, right? Then if we do some simple algebra, that we let this capital A minus small a and C, also C capital A plus A, then because it's 1 or -1, right? So the value of this A minus A could be 0 plus -2 or plus -2, 0, right? So only these 4 different possibilities, right? Then a little bit more complicated of the algebra is that we let A minus A multiply with B, capital B, and subtract this A plus small a and multiply with small b, right? Then you try this is a different value, 1 and minus 1, and you see this value then could be minus 2 or 2. There's only 2 possibility, right? So this is for one single experiment. You got the measurement outcome is a 2 or minus 2, right? So in principle, you have to do the experiment many times, right? So you take the average of this 2 and minus 2. Then, of course, the average value of these 4 terms is bounded by the value of 2, right? If you take the absolute value, right? But remember, this is under the assumption of the locality and realism, right? So before you measure it, it already has some certain value, 1 or minus 1, right? So this is a classical way, classical thinking. But in quantum mechanics, right, then your professor, your teacher will teach you that if you wish to calculate the expectation value, right? Now this A, B, this measurement are no longer the value. In quantum mechanics, they are observables, they are metrics, right? So if you wish to calculate this expectation value, you have to sandwich, right, the quantum state, right, cat and bra, right? So imagine now if in the central source we create a spin single state, it's a maximally entangled state. Then we sandwich this operator, say this a capital A and capital B, right? Then if we say this kind of measurement is try to measure the direction of the spin A and B, right? Then the simple calculation will show you that this is result is actually equal to minus cosine theta. Theta is the angle of this the 2 spin direction. Okay. So therefore, this 4 expectation value is actually a combination of cosine theta, right? Along different angle of the spin direction. So if you properly choose the measurement direction, say capital A is along X direction, and small a is along Y direction, and B is along, say, 135 degrees, and the small b is along 45 degrees, then the outcome of this, the average value using quantum mechanical calculation, you got a value 2 square root of 2, which is larger than the classical way, right? So this gives you a way to distinguish this quantum and classical situation, right? To see if this quantum mechanics is correct. That means if the assumption of locality is realism is right or wrong, right? Then actually in 1980s, people started to do this kind of experiment in the photon, entangled photon, and see the violation. But the people still arguing that when you do this kind of experiment, there are some loopholes on this experiment. So later in 2015, a 3 experiment demonstrate that okay, they have this at least to some point they have some loophole-free test of this Bayesian inequality. So basically, they cross the door on the Einstein and Bohr's quantum debate. Okay, so the quantum mechanics win, right? So, and this is a Bayesian inequality we learned in this quantum mechanics lecture. Now let's forget about the 2 particle. We just come back to consider 1 particle only. For 1 particle, we can also talk about this quantum correlation. That means we can focus on 1 particle and do the measurement. For example, do the measurement 2 times and to see if there's a correlation among these 2 measurements. So this is the temporal correlation. So speaking of the temporal correlation, we have to mention this Legge-Gauge inequality. Okay, so this is the inequality proposed by Tony Legate at 1958. So at that time, he imagined that imagine if you have some sort of a macroscopic object. Because this is a macroscopic object, for example, you can see you have a two potential well here. So because it's some in the spirit of macroscopic, so if you have a ball, it's either in the left well or in the right well, right? So there's you can assume there's a realism, you know, before you measure it, this ball is already in the left or right well, right? Then, and also because it's macroscopic, it's very close to our daily life experience. So in principle, you can perform the non-invasive measurement on this macroscopic object, right? Without the change the state of the system, because it's macroscopic object, right? So therefore, under these two assumptions, right? If you have an observable A, and this value is bounded by 1, by unity, right? So under these two assumptions, it's a realism, and in principle, you can perform non-invasive measurement, and you try to calculate the expectation value of these two time correlations, 82, 81, 83, 82. And 83, 81. So you have performed the measurement at 3 different times and try to look at the two-time correlation function, the average value, because this is the macroscopic object. So it should be bounded by the value of 1, right? But again, in quantum mechanics, right, this observable are not value, they are metrics, right? So in quantum mechanics, there's a way to see the violation of this inequality. Okay. So this is an experiment in 2010. So and the group using this superconducting circuit to try to look at this Legage-Garg inequality. And you see they have a point that's the violation is larger than the value of 1. So this is a violation of Legage-Garg inequality. So you see in the nature physics, they have a very good cartoon saying, okay, the moon is not there, right? If you do not measure it, okay. So later there are some more strict experimental tests on this macroscopic realism also in superconducting flux qubit, okay. So, so basically, if you won't wish to test this kind of the violation of this inequality, as a theorist, usually it's very hard to do this. But right now, we have this kind of device in the cloud. For example, the IBM quantum device, and some devices are free. You just register an account and log in, then you can use the IBM quantum device. So therefore, we came up an idea that we can try to test this kind of Legage inequality. So at that time, we play with this Legage inequality, but of course, a different kind, a variation of this Legage-Garg inequality, and we call this the quantum witness of this non-macroscopic case state in the cloud. So what I mean the case state in the cloud, that is in this device, we try to construct n-qubit GHD state. Right. So n-qubit GHD state can be written like this. So here you have a 0 and 1, and the cosine theta, sine theta, right? The angle you can tune in principle in the device. So n here is a number of the qubit you are using, right? So you have if n is 2, then there's a 2-qubit entangled state, 0011. And if a qubit number is 3, is a 000 plus 111, right? This is a GHD state. So this is a maximally entangled state. So how do we test this quantum witness for this LG inequality? So we have the case for the 2-qubit case, for example. So for the 2-qubit case, so it's simple. The idea is very simple. So for this 2-qubit case, let's look at the figure A. Then we initially set the qubit in the 0, 0 state. Then we perform some kind of the 2-qubit operation, say U, right? Then after the operation is at T1, okay? Then after T1, we perform its inverse, right? Then we perform some measurement. Then we say this measurement is performed at time T2, okay? So this is the first part. Then we do almost the same thing, the figure B shown here, but between U and the U inverse, U dagger here, we do some kind of measurement, right? We do some kind of measurement. Then after that at T2, we also do some kind of the conditional measurement of this. So if this non-invasive measurement assumption is correct, so the difference of the outcome of A and B should be 0, right? But if the assumption is wrong, that means the measurement at time T1 do have some effect on this, on this qubit. Then there's weightiness is not 0. Then you see the quantum mechanics govern this the evolution. So here comes the result. Okay, of course for qubit n = 2. You can see this violation. You see this blue dot here are the result of this quantum weightiness, which is the difference of these two situations. You see, of course, if you tune the angle theta to 0.5 pi, you see the maxima, the maxima, this weightiness. Then away from this yellow part, because the yellow part, you see the quantum weightiness is very small. It's the macro-realistic case is a classical situation. But you may say, of course, it's a two qubit is quantum mechanics. Then we can go to the higher number of qubit, say with a qubit number 4 and qubit number 6. Okay, so in our theory, we have derived a result that the weightiness here, W, has to be larger than we call it the measurement invasiveness. Then to show it's a quantum, we have to let the W larger than D. Of course, I will skip the detail here because of the time limitation. You just grab the concept of this. Then if W is larger than D, then we say, okay, it is non-micro-realistic, that is quantum behavior. You see, if we let qubit number go to 4, you see we have a weightiness larger than this invasiveness D. Okay, this is good. Again, this is quantum behavior. But if you go to qubit number to 6, then you see the weightiness becomes very small, and the measurement is larger, right? And in this case, we said it's not. We said it's 6-qubit system potentially admits a macro-realistic because W is not larger than D. Okay, so it's a classical description, right? So for this IBM device, if you go up to 6, you can no longer see this quantum behavior. So this is a test of the Legge-Gaon inequality. All right, so let's come back to this two-particle spatial case. Then this another inequality I would like to show you, or another quantum correlation I would like to show you is that the quantum steering. So how does this word steering comes from? So the steering comes from that actually when EPR, the Einstein, Podolsky, Rosen in 1935 proposed the challenge to quantum mechanics. Schrödinger gave a response. And he said that it's not the incompleteness of quantum mechanics. It's ability, because this entangled state, the Alice can steer Bob state remotely into an eigenstate of one of these. And he called this is a resource, entanglement. But at that time, he introduced the word steering, but he did not give any mathematical formulation of this steering. So until 2007, so a bunch of physicists write down this formulation of steering in a steering inequality. Okay, so now if you wish to describe the quantum non-locality or to describe quantum entanglement. There are actually 3 different ways to describe quantum non-locality. So the first way is figure A, the figure A. Then on the both hand side, Alice and Bob side, you trusted the measurement device. It's clear, no error and no cheating. Okay. So if you want to make sure if their 2 particles are entangled or not, you just do the measurement quantum state tomography. Then try to calculate how much the entanglement is, right? So this is the scenario A. And the Bell inequality I show you in the beginning is the figure B. That is, on both sides, you do not trust Alice and Bob measurement device. You are not sure if they are cheating you or not. So you ask Alice and Bob to perform some measurement, right? Then return to you their measurement outcome. Then you put their measurement outcome into the Bell's inequality. If violation, you have to admit, okay, their 2 particles are entangled. So Bell inequality is the most strict, okay? This is a third scenario we call steering, okay? So right now, Bob on the right-hand side, he trusted his measurement device, okay? His device is perfect, no cheating, but he is not sure if Alice is cheating her or not. So Bob asked Alice to do some measurement and can send to him her measurement result. And Bob himself, he performed his trusted measurement and put into the so-called, there's some kind of inequality similar to Bell's inequality. So I'm not going to show you the detail how to derive this. You can check this on the reference. So this, you see, P is the measurement outcome of A on L side probability, and B is the the average value of the Bob's measurement condition on Alice's measurement outcome. If this inequality is violated, Bob has to be convinced that his particle is entangled with the Alice's particle. So there is a hierarchy relation among 3 different forms of this non-locality or entanglement. So we can have an example to describe this. Then we can have this Warner state to test this hierarchy relation. The Warner state is a composition of a single state, the Bell single state, and the identity, right? Then there's a coefficient V, 1 minus V before them, right? If V is large, then we have a higher entanglement, right? Then if V goes to 0, there's no entanglement, of course. So this is very good example to test this how much the entanglement. Okay, if you wish to show this is the Bell non-local, it's a Bell violation state, then theoretically you need this V to be larger than 0.65 something. Okay, so this is the most strict. But if you wish to see the EPR steering, you only need this coefficient V larger than 1/2. Okay, then to show this non-separability, then is the least strict. You only need the V to larger than 1/3. Okay, so this is a hierarchy among these 3 different quantum correlations. So now here comes the puzzle. Okay, now on the top row, left-hand side, we have a 2-particle Bell's inequality, right? On the top row, right-hand side, we have a single particle Lagrange inequality, but perform measurement at different time, right? In the second row, left-hand side, we have a 2-particle steering inequality, right? On the second row, right-hand side, so we ask ourselves, do we have some kind of temporal steering inequality just like a Lagrange inequality? And the answer is yes. So we can borrow some idea from the Lagrange inequality. So we just focus on, again, a single particle, right? A single particle is sent into the channel. And Alice at the time TA, the earlier time TA, and she claims she can perform the non-invasive measurement. She claims she can perform non-invasive measurement at time TA. Then after her measurement, the very same particle is sent into the channel. Then a later time TB, Bob performed the trusted measurement, right? because the assumption is quite the same to the steering inequality, spatial steering inequality. So we can write down the same inequality for the temporal steering inequality. Okay, so this is a simple mathematical formulation is same. Then we don't need the integral photon to do the experimental. So therefore, in the experimental, it's easy to test. You see, in 2016, in a experimental group in Poland, they have shown this temporal steering inequality violation. You see this the square, the black square or black triangle are the result of the experimental data, and the black curve are the theoretical prediction. So you can see some violation of the steering inequality. And we can also quantify this temporal steering, okay? Then if you quantify this temporal steering, then you can use it to test the non-Markovian, or say quantify non-Markovianity. So what is non-Markovian? Okay, so a simple hand-waving explanation is like this. Imagine you have a system here, and you have coupled to an environment, right? So say, imagine you have a two-level particle, right? Put it in a free space. Then you have an electron in the excited state, then decay to the ground state and emit a photon, right? Then the photon goes out to the environment and then never comes back, right? So there's some parameter, just like the green curve here. It's a monotonic decay, right? Never comes back, right? So we say this kind of Markovian behavior. So, however, if you put this atom, two-level atom in a cavity, just as the previous speaker has shown you that the atom in a cavity, right? The photon bounce to the wall and reflect, may re-excite this atom, right? Then you see some parameter, physical parameter show you some revival, right? Maybe re-excite the population again. So you see some revival of some physical parameter. Then this is non-Markovian behavior, right? So in our case, our temporal scenario is like this, right? So at the earlier time, Alice performed a measurement X and get outcome A, right? So after her measurement, the state, the conditional state, sent into the channel, right? So later time, Bob performed the trusted measurement. Then he get this, we call this, in the language of steering, then we call this assemblage. So the assemblage, the meaning is that it's a subnormalized state. It's the quantum state Bob received, but multiplied with the probability condition on this Alice's measurement outcome. So for this kind of assemblage, then we try to use in a computational technique, SDP method, to try to maximize how much portion of this assemblage is unsteerable, right? Then the rest one, so mu is the unsteerable part, and the rest one is the steerable part. So the rest one, y minus u, is how much the Alice can steer above state, okay, using the quantum way, okay. So then we further shown that this kind of assemblage, okay, temporal stable weight, is a non-increasing function under CPTP map, or completely positive trace preserving map, okay. So this is a mathematical technique, okay. Once you have this, it's a monotonic decreasing, then under CPTP map, then if you, in your calculation, you find some increasing, then this is way to quantify. You just quantify the positive slope of this temporal stable weight, okay. So this is a mathematical detail. I don't want to go into detail. We can have a look at the example. So let's look at the figure A here. So if you imagine you have a two-level atom, so immersed in the Markovian environment, right? Then you see the temporal stable weight, which is how much we quantify the temporal steering. You see the monotonic decay, okay? So this is non-Markovian, no problem. But now, if you consider your system, okay, let's consider very simple, see, 2-qubit system, okay? Then you consider your left qubit is your system, okay? And the right-hand side qubit is your environment. So this is very strange way, but still you can look at your environment like this, right? So if your system, that qubit, has some kind of coherent coupling with your environment, the other qubit, right? Then you see, if you have a coherent coupling, then you find this excitation, right? It goes back, right? And go back between these two particles, right? And if you just look at the system and try to calculate its temporal stable weight, is how much the steering is. Then you see, initially it's a decay, right? You see the red curve here. Then after some time, you have some revival, right? You have increasing. That means the information flows back to your system. So you just integrate this a positive slope here, and you get how much the non-Markovianity your system has.
Active.
So then after our theory, then later is which is there's an experiment they demonstrate that also using the photon and immerse in some kind of non-Markovian environment. You see this dot are the experimental results. They clearly observe some revive of this stable weight. Okay, it's not easy to, which is easy to demonstrate. Okay, now we have a two-particle spatial steering, right? Now we also have a one-particle temporal steering. And then we can combine spatial and temporal. We have a spatial-temporal steering. Okay, spatial temporal steering. Then the idea is also simple, right? Now you prepare two-particle. Then Alice perform a measurement on the upper particle, right, at earlier time. Then after her measurement, these two particles are sent into a channel lambda. Okay. Then after some evolution, okay, then Bob at a later time perform his trusted measurement, right, on the lower particle, right. Then this constitute this spatial temporal steering. Okay, the mathematical structure is almost the same. So then the function is that the spatial temporal steering can be used to test. Imagine if you have a network here between A and B, there's some network connection. If you want to test whether there's some quantum damage, between this network, you just test the spatial temporal inequality of A and B. Then you can see if they are quantum connected or not, or if they are classical damage. Okay. So because of time, I'm going to skip this. Okay. So anyway, I hope through this introduction, I hope I have convincing you that quantum steering, no matter spatial or temporal or spatial temporal, is a resource. Okay, it's a resource can be used to do something, to do some quantum task. For example, I have no time to explain is that in this talk. In this paper, recent paper, PIS Quantum, we have shown that we can use temporal correlation to quantify quantities of a channel without using entanglement, because entanglement is some kind of a precious resource we want to preserve. We can use a temporal correlation to quantify the quantities of a channel. So now I'm going to show you the application of this spatial temporal steering. The first application is we can use it to benchmark the quantum state transfer in this quantum device. As I've told you in the very beginning, right? Right now we have this different quantum device. We can either access it freely or we can pay the cash to use it. So IBM Q is free, and IBM Q you can pay and you can use it. Also, we have a QTech devices are for right now there are many devices in the cloud. So we have this spatial temporal steering, right? So we prove that if you have a spatial temporal steering perfectly, then it is actually identical to the quantum state transfer. So what is quantum state transfer? So the idea is simple. So let's look at the left figure. Okay, you have the blue particle and green particle. Okay, initially you have the blue particle at state low A0, right? Then This you send this two particle into a channel. Then after some evolution, right? You wish the state rho A is transferred to this green particle, right? After the evolution. So this is the idea of the state transfer. And then you see it's really similar to the spatial-temporal steering. I just introduced that. You see, temporal steering is that Alice perform a larger, earlier measurement at earlier time, right? Then after her measurement, these two particles are sent to the channel, right? Then after some channel, Bob on the right-hand side perform the trusted measurement, right? So it's very simple. So we sort of prove that to have a perfect quantum state transfer is equal to have maximum steering. So there are different ways to quantify the steering. So now in this later work, we use the robustness. It's actually identical to the steerable way. But for the moment, you just remember it's just a quantifier of how much the steering is, okay? So, but if you play with this steering stuff, there's one issue arise. That is the no signaling issue arise. Why? Because when we consider this Bayes inequality, no matter it's Bayes inequality or the EPR steering inequality, actually there's an assumption. There is under perfect condition, Alice should not signal back, right? That is, even if they are very far away, Alice cannot signal back. So this is no signaling. But in this cloud quantum computer, IBM Q, Q, they are not perfect. Okay, so there is a chance that Alice can signal back classically. So when you play with these steering things, you can quantify how much the signal is. Okay, this is D. So I just skip this investment detail. You just know we can quantify the signaling effect when you play with this steering theory. Okay, so what we want to do is that in this device that we have a string of qubit from Q1 to Qn. Now we wish to transfer our quantum state from qubit 1 to qubit 2, then qubit 3, and later to qubit n by turning on the adjacent interaction between two qubits. Okay. Then this is the circuit diagram we have. Okay, so initially we prepare our state in qubit 0, right? Qubit 1, sorry, 0 state in qubit 1. Then we perform some 2 qubit operation on qubit 1 and qubit 2. Then qubit 2, qubit 3, and so on, so forth. Then to qubit n-1 to qubit n. Then on the qubit number n, we perform the measurement, right? Then we have this spatial-temporal steering. So under the ideal case, perfect case, the device is clean, no signaling, is perfect. Then no matter how long the number, how many number of strings you see here, the black, blue, red, and the green are the result for n2 to 5, right? And then you choose. Then in this device we have this control rotation theta. You choose, if you choose your theta angle here is equal to pi, then you always reach the maximum value of the steering, which is 0.26. Remember now the maximum value of steering is 0.26. Okay, so if the perfect case, you always reach the maximum. But in real case, it's not the case. You see, here's the other experimental result on IBM Q. Okay, we test it on IBM Q Bablingen. Let's look at the figure B first. And this is the result on January 2020. And this is a black, blue, red, and green dot are the result for qubit number. Transfer your qubit to 2, 3, 4, 5. And you see when you increase the number of strings, the magnitude decrease, right? Then at a later time, on March, we performed the very same experiment on the very same device. Then you see the steering robustness. You see this black, blue, red, green. Also, this decrease, right? When you increase the number of qubit string, it seems no difference, right? Oh, I forgot to mention that after January, they perform, in the IBM team, they perform some calibration on their device. If you just look at the figure B and figure A, and you will see it seems no difference after they do calibration. But if you look at the signaling effect, then you observe there's a difference. You see, it's a figure C and figure D are the signaling effect. We can quantify. That is how much the Alice signal bar, right? This is something we don't want, right? You see, you look at the figure D here. Before they do calibration, you see there's a huge signaling effect. This is bad. This is something we don't want, right? But after their calibration, okay, you see their signal effect is greatly reduced, okay? So you see the calibration works, right? Although even the magnitude of steering doesn't affect too much, but the signaling effect is greatly reduced, okay? So that means the steering theory can be used to benchmark how good the performance of this the quantum state transfer, okay? So we can also play this the state transfer on different quantum device. So we can look at the result on IonQ device. So you see, this is IonQ result, and we only have 2 results for qubit number 2 and qubit number 3, and the blue curve and the red dash curve are the theory, and the blue dot and red triangle are the experimental result. You see. Then you see the upper figure is the how much the steering is, okay? Then almost you see there's at c equal to pi, there's a maximum value, but you see the signaling effect is kind of random, right? In this IonQ system, it's maybe due to that this IonQ system is made of ion, right? If you wish to control control the quantum state, some of the steps to use the vibration of this ion, right? So if you, for example, if you try to control the quantum state of one ion, you shine a laser pulse, right? Maybe this the vibration of this ion can affect this adjacent ion, right? Then induce some signaling effect, right? So you see, you can imagine this in the ion system, the signaling effect is larger. Okay. So here are some comparison between different devices. You see, you have IBM here. You have a QTech in the middle. Also in the lower panel, you have an IonQ system. So overall, if you overall look at this, the data you have, you can see. In average, the IBM Q system has a better steering robustness. That is the better steering, which is good. And the second one is the IonQ, right? But speaking of the signaling effect, right? IBM Q is the best, but the IonQ is sort of too large. So this for the moment, from our data, we can tell you the performance of 2 different devices. Okay, so the second application I would like to tell you is that we can use this quantum steering to witness quantum scrambling. Okay, so what is quantum scrambling? Okay, so quantum scrambling it describes how your information is delocalized among different qubits. Okay, we can have a look at this example to see the quantum scrambling. So imagine you have 5 qubit system. Okay, so initially you have your information stored in the qubit 1. Okay, then you let this 5 qubit going through some unitary evolution. So remember, it's a unitary evolution. Okay. So after some unitary evolution, right, then you will find the information is delocalized in general, it's delocalized to this distributed to this 5 qubit. So quantum information scrambling describe the delocalization of local information original in Q1 to a global information. Then you spread the information to this 5 qubit, right? In the form of entanglement. So this is the physical, description. So I skip this mathematical formulation. So a simple example is that for this 3 qubit system, okay, 3 qubit is we call this a QFort scrambling circuit, okay. So among you see this 3 qubit system, you can this QFort scrambling circuit, you can play with this 2 qubit operation on 1 2, then 1 3 and 2 3, then control Z rotation is a bunch of this kind of 2 qubit operation. Then you see this information originally A is delocalized into 3 different qubit. Then you can quantify this information scrambling. You can try to in the end you can separate the system into 2 parts. That's part C and part D. So part C is the original single qubit, and the part D is the second qubit and third qubit. So therefore, you can use we call it tripartite mutual information. That is the A to CD, okay, the total. Then subtract A to C and A to D. So the detailed description of the mutual information, please check the Google, the Wikipedia, and you can find this how to define the mutual information. It's okay. So you in a sense, just the total just A to CD, then subtract the individual information. Then you can quantify this the scrambling among this 3 qubit. So you see, if you probably tune this as angle theta, then you see if the angle theta is equal to pi over 2 or 3 pi over 2, you reach the black curve is the mutual information, tripartite mutual information. You see the maxima, the maxima information scrambling, okay? And in theory, we also proved that we can use this spatial-temporal steering to witness this the scrambling. This is the result in dash curve. You see we have a total, that is a spatial-temporal steering, A to CD, and subtract A to C and A to D. And then you get this witness. And this result is shown in the red curve here. Okay, so in principle, basically you can catch the main feature of this scrambling. Okay, another one to verify this the quantum scrambling is that you can use quantum teleportation to verify the quantum scrambling. So the picture I show you is the experimental result by Christopher Monroe. They used a 7 qubit system to demonstrate this teleportation. So initially, you see on Eddie's side, she has this, you see the qubit 1 to 3. So on the Bob side, he has the 4 to 7, right? And initially, this qubit 2 and qubit 5 entangled, and qubit 3, qubit 4 entangled, also qubit 6, qubit 7 entangled. Then on Alice's side, she encoded her information on the qubit 1. So these 3 qubits are sent to a scrambling matrix. You can, just the unitary matrix for this 3 qubit system. But for the Bob side, he used the U dagger, this unscrambling matrix on this particle 4 to 6. Then if Alice can successfully teleport her qubit to the Bob's qubit, which is qubit number 7, in the end, that means theoretically they prove that means this U is really a scrambling matrix. Then that means the scrambling really occurs on this 3 qubit, okay, using teleportation. Okay, of course, I skipped the mathematical detail. You can have a look at the paper. So this is the 8 by 8 matrix of this unitary matrix, and the detailed circuit is like this. They have a 2-qubit operation, also have a Hartmann single qubit operation. The detail you can check this paper. And you see their result on teleportation is about 80%. Of course, it's larger than 2/3, right? So it's they say, okay, in this 7-ion system, they really observe this quantum scrambling. Okay, then now we have a cloud computer in the like IonQ. So we sort of try to redo this experiment in this IonQ system. But the difference is that we use a simplified circuit. So we just only use a 5-qubit system, okay? But the mathematically, this is the same, identical to this previous 7-qubit scrambling case, okay? Then we try to redo using this 5-qubit, try to redo this teleportation. Also, you see, teleportation is also, you can view teleportation is some kind of state transfer, right? The state transfer from Alice to Bob, right? So since it is some kind of state transfer, then we can play with this spatial-temporal steering, right? That means perfect teleportation is perfect state transfer. Then you have a perfect spatial-temporal steering, right? So you see the lower panel, the data is the teleportation fidelity we have. So we have even higher teleportation fidelity. Some data are almost to 90%, okay, on this IonQ device. But as I said, we play with this steering. You see, our steering here from Alice roll in to roll out is 0.091, which is not very good, okay? But still, you have some finite value. But the problem is that we can quantify the signaling effect, right? And we observe that there are signaling effect in this IonQ device, which is 0.085. It's almost the same to this the spatial-temporal steering, right? So that means this IonQ system, when you play with this some quantum text, even for the scrambling, you see this unavoided signaling effect. This
Cheng, could you please complete it so that we have some time for discussion? There's
okay.
Some question,
so answer the question, right? I guess.
There is some question in the chat box.
Okay, sorry. So I should, okay. So I have a question. Can temporal quantum steering be applied to quantify inseparability, non-classical correlation of a temporal mode? Can temporal non-cross? I think in principle, yes. Okay, just the result of a temporal multiple squeeze. But if you're talking about screen vacuum state, so because now here we just play with this qubit, this two, this I'm not sure. Of course, in principle, I believe yes, you can write down the temporal steering for this maybe for Gaussian state, but I'm not sure for the squeeze state. So I am not quite sure. Okay, temporal cluster state. I remember I have observed this Gaussian spatial steering, but I haven't seen this Gaussian temporal steering. But squeeze state I do not know. Okay, but I believe I think it is possible. Okay. Okay, so let me continue. So basically we have a signaling effect in this device. Okay.
So there's some question in the chat box. Can you look into it and respond?
So some
in the chat box, there are few questions I did not.
2 questions. Okay.
Yeah, in the chat box. You can look into the chat.
Text box.
Yeah.
Yeah, just one question I saw.
Yeah. Could you
temporal mode cluster state? I'm not quite sure, but I believe you are, in principle, you are able to construct some steering inequality or to take this temporal cluster state. Okay, so because of time limit, I guess I'll just simply show you that the third application is that we can we can use this steering to do some quantum metrology. That is, in the paper last year by Yueh-Nan and his collaborator, they have shown that if on Bob's side he generate from some operator, he generates some phase shift. Then depending on the Alice measurement result, he can decide to predict this phase or predict this phase or estimate this phase from measurement N, or or measurement is H before, and they have another steering inequality. Then that is you see this F is the visual information. Basically, it's visual information. It's smaller. It's bounded by the 4 times the variance of this. A is the assemblage I just mentioned before of this assemblage A, and this H is observable, which generates this phase. Okay, if this steering Alice Bob is unsteerable, then the inequality is obeyed. But if Alice can steering Bob, then this inequality will be violated. So in some sense, this is another steering inequality. But this physical meaning here is that if violation, you have a larger visual information, and larger visual information is good in quantum metrology. Okay, if you are interested in quantum metrology, you can check this also in the Wikipedia and the simple explanation. That is, in principle, you have a larger visual information is good for quantum metrology. And anyway, we try to play with this also in the IBM system, and we find this you can see the violation of this. Okay, I have no time to describe the detail. And then here's a circuit to test this steering enhanced metrology. And here are the experimental results. You see this when the red dot is larger than this variance, the blue dot, and you see some advantage of the metrological, the steering enhanced metrology, steering enhanced metrology. Okay, so yeah, because of time, I come to the summary. Okay, so I've shown you the steering is a resource, and you can quantify non-Markovianity and its application. You can benchmark quantum state transfer, and the witness scrambling. Also, you have some application in quantum metrology. Okay, so this is the end of my talk.
Thank you, Professor Chen, for a really excellent talk. And maybe you can take 1 or 2 questions if somebody is willing to ask a question. Is there any question from audience? I think there is nobody interested to ask a question. So let me thank you again for a beautiful talk. Thank you very much.
Thank you very much. Thank you for your attention. Thank you.
So now the third speaker. So let me see. Oh, so Himadri Sekhar. So the third speaker in this session is Dr. Himadri Sekhar from the IIT Bombay. Please share your slides.
Yes.